In this lesson, we're going to learn to draw Lewis structures for covalent compounds. So what is a Lewis structure? Well, a Lewis structure is giving you a little bit more information about the compound than just a formula does. So a formula like NF3 is telling you that there are 3 fluorines in the molecule, but it's not telling you at all how they're arranged. Like, say for instance, if you had, and let me change my marker color here, let's say maybe you have the 3 fluorines kind of trailing behind the nitrogen like that, sort of like a train, or maybe the nitrogen's kind of in the middle with 1 fluorine on one side and a couple of fluorines on this side. That's what I'm talking about as far as an arrangement goes. So a Lewis structure shows you exactly how the molecule looks if you look inside the formula. Now this is what NF3 really looks like. The fluorines are spread around the nitrogen. If you're wondering what SO2 looks like if you draw its Lewis structure, this is what its Lewis structure looks like. If you draw this compound over here, which is called hydrogen cyanide, that's its common name, that's what it looks like. And you're going to notice some interesting things about this is Lewis structures don't just show you where the atoms are, they also show you where the electrons are. So super important to understand about Lewis structures is they show how atoms are arranged and how electrons are shared within those molecules. So we've seen that a molecule can have a single bond, and when I say single bond, it's really important to understand that when we're looking at a single bond, which obviously is one line, that's a covalent bond. It's not an ionic bond. We're not going to do any ionic compounds here because that line represents something specific. It represents the sharing of 2 electrons. The sharing of 2 electrons. One of those electrons came from the fluorine, and one came from the nitrogen, and the bond, as all bonds do, are connecting them together. We have bonds with our family and friends. Well, that's the bond that keeps the 2 of them together, and each one of those lines represents a covalent bond, and there's 2 electrons in it. So if you get the idea, any guess how many electrons are holding together this sulfur and that oxygen in that double bond? The answer is 4. There are 4 electrons, 2 in each one of these bonds, and there are 4 electrons. How many electrons are holding together this carbon and nitrogen? 6, right? There's 6 electrons in that triple bond. Now, as you can imagine, triple bonds are much stronger than double bonds, which are much stronger than single bonds. The more covalent bonds holding 2 atoms together in the molecule, the stronger that bond will be. So if you were going to try to break a bond in this molecule over here, if you were trying to break bond A or bond B, A would be much easier to break because it's a single bond. So that's really important to understand, is that each one of those lines represents a covalent bond, not an ionic bond, and there are 2 electrons in there. Now what about the rest of these electrons? Well, just like the electrons in the bond where there's 2 of them, you notice that all the other electrons come in pairs. We refer to those as either lone pairs of electrons or unbonded or non-bonded electrons. And what we mean by that is there are electrons that are holding the sulfur and oxygen together, they're bonding them, but this pair of electrons right here, it's a non-bonding pair of electrons, or a lone pair of electrons. So that's how we'll represent those, as little dots. So how can we predict what the Lewis structure will be for a compound? Well, there are a set of 4 rules that a person named Lewis came up with that are very predictive of the shape and arrangement of the atoms in a molecule. These 4 rules, it's important to understand, they have to be done in order. There's no switching them around. So it's really important to know that. Now, yes, I would recommend you get these in your notes, but I'll tell you, we're going to practice them so much, it's likely that you'll just know them. Okay, so let's start with this. So we got to go back to rule number 1. So rule number 1 is count the total valence electrons in the molecule. If I go back and show you these molecules, it turns out all of these electrons, it didn't matter whether they were a lone pair, a bonding pair, a double bond, all of those electrons were valence electrons. They're the electrons in the outermost shell of oxygen or sulfur or any atom we're talking about. So that means we got to go back and revive how do we actually figure out the number of valence electrons in a molecule. So let's do this. How many valence electrons will nitrogen contribute? I'm going to put up here valence electrons. Well, nitrogen will contribute 5 valence electrons. How did I figure that out? Well, the first thing is I had to convince myself that the answer is not -3. That's the charge of nitrogen, and these are not ionic compounds. We're trying to figure out how many valence electrons there are, and it's been a while since we've looked at this. Nitrogen is right here. What shell are its valence electrons in? Well, they're in the second shell. You remember the rings represent the shell? There are 2 shells in nitrogen. And the way I figure out how many valence electrons there are is I count columns. 1, 2, 3, 4, 5. There are 5 valence electrons. If that's true, each fluorine will contribute, there's fluorine, how many? 7. 1, 2, 3, 4, 5, 6, 7. Now, of course, there's more than one fluorine in this molecule. You'll see over here there's 3. So each fluorine will contribute 7 valence electrons. Now what we're going to do is we're going to add those up because the molecule itself has to arrange all of its bonding and non-bonding electron pairs out of those total valence electrons. So if you add those up, you'll come up with 26 valence electrons. By the way, this is a pretty good number. And the reason is because if electrons come in pairs, your total has always got to be an even number, right? Not an odd number, not like 3, 5, 7. It's not going to be odd. Now I put that little star next to that to remind myself to say to you, can a molecule ever have odd numbers of electrons? Yes, there are things called radicals that can. You will not see them in this course, but be aware if you go off and study chemistry at college, there are these things called radicals. But for us, if you see an odd number, recount your valence electrons. Something's wrong. Okay, step 1, done. We've figured out how many valence electrons there are. All right, step 2, arrange the molecule with the single atom in the middle. So I'm going to draw the molecule, and I'm going to put N in the middle. Why? Because N was the one there was only one atom of, right? That's what it's talking about with single atoms, right? So I put N in the middle. In that previous one, we saw SO2 a moment ago. I'd put S in the middle because there's only one S. All right, we did step 2. Boom, done. Let's keep going. Step 3. We are going to start on the outside of the molecule, and we're going to start adding electrons to it. We are going to add electrons until each one of those outside atoms has 8 electrons. Now, I want you to see what I'm doing here. You remember that when we did electron dot models, I put these little boxes up here, and it was just to make sure that everybody understood there was a top, bottom, left, and right. And each one of those boxes, which we formally call an orbital, has 2 electrons in it. So we sort of went around the outside like this, right? And then we found out we had to pair them at some point, right? And the goal was to get them so that they all either gained or lost electrons. So they had 8 electrons and were isoelectronic with a noble gas. Now the reason fluorine is getting into this relationship with nitrogen and the other fluorines is because they promised it that it would have 8 electrons. So our job is to go around the outside of the molecule and make sure they all have 8. Now the good news is if we have a top, bottom, left, and right, do you see this fluorine down here? It already has electrons on the right. How many electrons are in that line? 2. There's 2 electrons in that bond. So this area over here already has 2 electrons. All we have to do is add 2 electrons to the top, the left, and the bottom. 2, 4, 6, 8. That's a happy fluorine. Let's do this one down here. You see these electrons on the top? We don't have to do there. We just have to do the side and the bottom and this side. 2, 4, 6, 8. Boom, good to go. Let's go over here. We don't have to do the left. That one's already done because they already have bonding electrons there. But I'm going to do the bottom, the right, and the top. 2, 4, 6, 8. Good to go. Now, before we go on to step 3, I want to see how many electrons we have left. We've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've used 24. How many electrons do we have left? We only have 2. We have 2 electrons left. That's all we've got. All right, let's go on to step 4. So step 3 was to go around the outside of the molecule first. And as you probably can guess, step 4 is then go to the inside and make sure that inside atom also has the satisfied octet. Now, you can see right now nitrogen doesn't. If I were to think about nitrogen's electron dot model, right now we're to put its boxes there. Right now it has electrons on the left, bottom, and right. In other words, this one's full, that one's full, that one's full. It has 6 electrons, 2, 4, 6, but it doesn't have any on top. It has an empty orbital. Well, the good news is we have 2 electrons left, so we can come in here and put those 2 electrons there. Now, lastly, it's a tradition when you're done to obviously check 2, 4, 6, 8, yep, 2, 4, 6, 8, and only on the central atom, put a little loop representing the orbital around those electrons. If there were 2 pairs of electrons, I'd have one loop around this pair and one loop around that pair. That represents the orbital. And we're done. We have a great Lewis structure. It looks like this. And if I were to ask you some questions about this Lewis structure, like how many single bonds are in NF3? Well, the answer is there are 3 single bonds. One there, one there, one there. How many lone pairs of electrons are on the central atom? Well, 1. Just like you're wearing 1 pair of shoes right now, there's 1 pair of electrons, unbonded or lone pair electrons on that central atom. Now, I bring this up because we're going to ask you questions like that, and I want to make sure you're familiar with that language. And there we go. We start step 1, count the total valence electrons. Step 2, arrange the molecule so that the atom where there's only 1 of them goes in the middle. Step 3, arrange them. Ooh, step 3, do I go on the inside or outside first? Outside first, and then step 4 to the inside with the goal. I always have to check, do they all have 8 electrons? Now, the ones we're going to do today are pretty simple, but we're leading up to, there are going to be times when they don't have 8, and how do you solve the problem? So getting in the habit of checking to see if they all have 8 is super important. All right, let's try this one out. So in this one, and we may have to move me down here so we can see our periodic table. So I've got the steps here. Let's start with this. I want you to count how many valence electrons oxygen has. Click on it right now. How many valence electrons does each chlorine have? And so therefore, what are the total number of valence electrons in this molecule? So this is how we do it. If I have oxygen, it's going to have 6 valence electrons. Why? Because it's right here. They're in the second shell, 1, 2, 3, 4, 5, 6. Each chlorine is going to have, and there's 2 of them, right? Each chlorine is going to contribute, whoa, its electrons are in the third shell, but still 1, 2, 3, 4, 5, 6, 7. Each one's going to contribute 7. And then we got to add it up. 7 plus 7 is 14. 14 plus 6 is 20 valence electrons. Hey, is this a good number? Yes, because it's even, right? Seems like a good number. So we must be on the right path. Boom, step 1 done. Step 2, arrange the molecule. All right, do you want me to put O or Cl in the middle? O goes in the middle. Cl I can spread out. I'm going to spread them out as far apart as I can, which is generally a good habit, but not necessary. If you had them at 90-degree angles, that's okay, but generally you want to spread them out as far as you can. All right, step 2 done. Step 3, do we start on the inside or outside? The outside. So that means oxygen or chlorine? Chlorine. All right. It already has electrons on the right, so it's going to need electrons on top, left, and bottom. Boom, 2, 4, 6, 8. Good to go. This one needs them on the top, right, and bottom. The left already has 2 electrons. 2, 4, 6, 8. We've used 2, 4, 6, 8, 10, 12, 14, 16. How many do we have left if we've used 16? We have 4 left. Now we get to go to the inside and make sure it has a satisfied octet. It has 8 electrons. Let's see, right now, before I do anything, how many electrons does the oxygen have? It has 4, 2 there and 2 there. Remember, it's as if its electron dot model has electrons on this side and this side, but not on top and bottom. So it only has 4. So therefore, let's fill it in. We've only used 16. We have 20. That means we have 4 left. I'm going to put 2 there and 2 there, and the oxygen has a satisfied octet. Boom, we're done. Let me ask you some questions about it. OCl2, based on its Lewis structure, how many single bonds does it have? 2. How many lone pairs of electrons does it have on its central oxygen? It has 2 lone pairs of electrons. Now, if you said 4, that's because there are 4 electrons. Like if I said to you, how many shoes do you have? You say, I have 2 shoes. How many pairs of shoes? You only have 1 pair of shoes. So we've got to put our little orbital loops. We only do this around the lone pairs on the central atom. There we go. So there are 2 lone pairs of electrons. Let's try another one. CBr4. Now I want you to work ahead of me. Ooh, I need a periodic table. There's a periodic table. Work ahead of me. I want you to add up how many valence electrons the carbon brings, the bromines bring, and put in the total right now. All right. So I'm going to say carbon is going to bring in 4 valence electrons, each bromine. I write these out. You could do bromine times 4. There's nothing wrong with that, right? I'm just writing it out to be clear. Let's see. Bromine would bring in 1, 2, 3, 4. You remember this is the part we don't do. 1, 2, 3, 4, 5, 6, 7. Each bromine would bring in 7. Can't have more than 8 valence electrons. If you have more than 8, something's wrong. If I add them up, 7 times 4 is 28. 28 plus 4 is 32 valence electrons. Hey, there we go. Even number. Step 1 done. Which atom do you want me to put in the middle? Carbon, I agree with you. Spread them out, and I want you to draw the Lewis structure. You're going to start on the inside or outside? The outside, definitely. Until bromine has how many electrons? 8. And then you go to the middle and see if it needs more. Okay? And then I want you to answer this question. How many single bonds are in your molecule? 4. How many lone pairs are on the central atom? 0. There were none, right? All right, let's see how this works out. Carbon goes in the middle. Wish I had drawn that bond a little bit better. It's meant to be connected to that. And there we go. Pretty good. Now we've done that. Step 3, go around the outside. This one needs some on the left, top, and right. Boom, 2, 4, 6, 8. Top, left, bottom, 2, 4, 6, 8. Top, bottom, right. And this one already has 2 electrons, so 2, 4, 6, 8. Bottom, right, left. 2, 4, 6, 8. We've used 8 around each bromine. 8 times 4 is 32. We've used them all. They're gone. All right, now I go to the central atom and see if it has a satisfied octet. Does carbon have 8 electrons? Yes, it does. 2, 4, 6, 8. It already has 8 electrons, right? In other words, its top box is filled by this one. Its left box or orbital is filled by that one. Its bottom one is filled by that one. And its right one is filled by that one. Now, of course, you might get to this point and you might say, hey, where are those double bonds? Where are those triple bonds? Those are coming up. We're starting with the simple ones, but those are coming up, and why we need them will come up quickly too. All right, I want you to try this one. Since you're getting good at these, I want you to first add up the total valence electrons. Let me get you a periodic table and type it in now. Secondly, which atom are you going to put in the middle? Yep, sulfur, definitely. Okay, oh, by the way, let me give you the total valence electrons. Sulfur, I get 6 valence electrons. Bromine, I get, for each bromine, I get 7. 7 plus 7 is 14. 14 plus 6 is 20. Okay, so we've got that. Now, I want you to draw the Lewis structure. Remember to start around the outside, then go to the inside, and I want you to answer a question in just a second. Okay, so the question is, how many let's go with that. How many lone pairs of electrons were on your central sulfur? Okay, let's see if you were right. Sulfur, bromine, bromine. I start on the outside, top, left, bottom, top, left, right, bottom, and the other side is filled by those two. I've used 2, 4, 6, 8, 10, 12, 14, 16. 16 electrons I've used. If I've used 16, how many do I have left? I have 4 remaining. Okay, and then we get down to step 4, go to the inside. Is the sulfur happy right now? And I don't mean to say happy, that's not what I mean. But you know it got into this to have 8 electrons. How many electrons does it have right now? It only has 4 electrons, that's right. Now the good news is we have 4 electrons left over. So I'm going to go to the top, I'm going to go to the bottom. Now you might at this point say, hey, can't I just run in there and just throw electrons on the sulfur till it's happy? Or until it has a satisfied octet? And the answer is no. It's just because we haven't run into any examples yet that there aren't enough electrons. We're going to have to deal with that. That's coming up. Sorry, I didn't give you a periodic table. I want you to type in how many valence electrons this molecule had to work with. Okay, I got silicon is 4 valence electrons. Let me see if I'm right. 1, 2, 3, 4. Yep. Chlorine, there's 4 of them. And you could write chlorine times 4. You don't have to draw it out. I'm just being explicit. And I got 7 for each one of these. Right? 1, 2, 3, 4, 5, 6, 7. Very good. 7 times 4 is 28. 28 plus 4 is 32. Actually, we're going to do one more beyond this. Okay, so now that you are sure you got the valence electrons correctly, I want you to draw the Lewis structure and answer this question. How many single bonds were in this molecule? 4. How many lone pairs were on the central atom? 0. Let's go check it out. All right, do you think that I should start drawing my electrons on the silicon or chlorine? Chlorine, because it's on the outside. I go like this. Top, left, bottom. Left, bottom, right. You get the idea. I'm essentially filling in all the orbitals that are empty, that don't already have electrons. 2, 4, 6, 8 around each chlorine. 2, 4, 6, 8, 2, 4, 6, 8. 8 times 4 is 32. We've used them all. They're gone. Now we got to check at the end. Is the silicon happy? In other words, does it have a satisfied octet? Yes, it does have 8 electrons. 2, 4, 6, 8. We are done and good to go. All right, our real last one here. You need a periodic table. There it is. This one, I want you to go through the whole thing yourself. I want you to add the valence electrons, draw the Lewis structure in your paper, don't guess. And then I want you to answer this question about what it looked like at the end. All right, let me show you what I came up with. Phosphorus had 5 valence electrons. Each fluorine had 7. 7 times 3 is 21. 21 plus 5 is 26. Hey, there's a nice even number. Okay, I'm going to put phosphorus in the middle because it was the central atom. That's a terrible bond, but you'll work with me on that one. All right, now are we going to put electrons around the phosphorus or fluorine first? Outside, so fluorine, top, left, bottom. You get the idea. Just filling in those empty orbitals. All right, we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've used 24. How many do we have left? 2. And the good news is now we go to the end. Before I do anything else, how many electrons does the phosphorus have around it? It's 2, 4, 6. It does not have enough. But the good news is we have 2 left. So I'm going to put those on the top to fill that empty orbital. And boom, there we go. Yes, there was 1 lone pair of electrons on the central atom. There were 3 single bonds. And that's how we draw simple Lewis structures. Now in the next lesson we're going to get to, actually probably first, what are some exceptions to the octet rule? That's the first thing we're going to do. And then after that we're going to get to, well, when and where do these double and triple bonds show up? Great job.